Hello, welcome back to our channel. Please subscribe Baba Kunde Kukola. So here is the second part of my video on advanced dynamic control of AEM electrolyzer model in ACM and Simulink. So in the first video, I discussed on how to create a dynamic controller for Aspen Custom Modeler model. So in the Aspen Custom Modeler model, I created an AEM electrolyzer, that is Anode Exchange Membrane Electrolyzers model, using the equation and the code in a nonlinear model that is very that the degree of nonlinearity is very large, because there is a from its algebraic equation there is logarithmic, like from over potential. There is non-linear equation, like there are some linear equation, there is over potential equation, there is dynamic equation, there is how will I call this, pressure drop code, if statement for some pressure drop code. So it is actually a system that calculates the hydrogen production process chemistry of electrolyzer, and there is a utility stream that is used to control the electrolyzer. For the system, I designed a controller. One is the discrete controller, and the other is actually analog controller. For the first video, when I tested the two controllers, there is a lot of error. The model is not working fine. So I think what happened in the video is the load on the Simulink is too high. So I'm going, instead of putting all the two controller together in the Simulink, I am going to remove one and run the model again. I'm going to remove one and run the model again, you understand, and see what. So when I run the model, the load on the Simulink is not fine, is not as expected with the dynamics, and with one is a discrete system. You're having a controller that has feedback and integration inside. So I am going to do it in different file in order to make sure that the system is working fine. So we run the analysis, you understand, the simulation again. So I'm going to be doing this by deleting this. So that's why I make this video. So for the first model here, so I'm going to be deleting the algorithm, so and saving the model as a new file. So I'm going to save it as B. So this will be B. So after saving it as B, I can now test the model. You can see it's from 3 to 500. You can see 3 to 500. So I'm going to test it from 3 to 500 and see how it works. So currently is 0. Okay, it's picking up a little bit. Okay, it's about later. It's about to be complete. Okay, it's done now. And the thing I want to explain is it's different from what we have before. I think the sampling was done wrongly before the when we are using the two controllers, because of the Simulink model is not even correctly, working correctly. You understand? I think it's from the Simulink relay, so it's not interacting, sampling the Aspen Custom Modeler block well. So the result is not done correctly, and the input is also wrong. That's why we are having all those no errors like no convergence. You understand? Instability in the results that we saw in my first video on this topic. So but here, after reducing the load on the Simulink, we can get the way the controller is going to respond. So you can see it's also force order. There is drop in the temperature, then the temperature return back, then you have the response here. So it's not wrong like the way it was before. So and we can even try to step it up from 5,000 to, let's say, from 3,000 to 5,000 back, 3,000 to 5,000 back. Let's step it from 3,000 to 5,000, and we see the response. You can see from 3,000 to 5,000, we see the response from the controller. So it's loading. So it's picking up. Okay. So it's done. The design is like this. So it increase, then it come down to 65 that we want it to be. So you can see the control is actually stable, and this is like this. And you can see the sampling time is one time step. So it's going to be doing the sample in each of these time steps. So I can try to increase the sample 0.5. I can make it to be 1, and we can check the response using one sampling time. So using one sampling time, I can check the response of the controller. So it's done. So this is the final error using. So it's basically like this. You can see the controller is more discretized now. So the result is more discretized now, and you can see the response from the from the from the system. It's come back to 75. So all this time can be used to adjust the controller and the lights. So the next thing that I want to try now is instead of having this step input, we can use like a sine wave generator for the power between 3,000 and 5,000. So for the power to and see the way the controller is able to manage it for the discrete. So I'm going to use sine wave. It's going to be a continuous sine wave, not discrete one. Okay. So I'm going to flip the block and connect it to this one. So the amplitude is going to be 3,000 to 5,000 to 5,000. That's 2,000. So the amplitude is going to be 1,000. 1,000. The bias, okay, can make it to be 0. The bias can be 0. Then the frequency, we can make it to be 1. Mm, can make this frequency to be 1. The bias will be 3000. No. It's going to be 4000. 4000. So the bias will be 4000. So then if it is discrete, so I want it to be continuous. Okay, I can make it to be discrete, maybe one I can make it to be discrete by sampling it in one time. So it's going to be discrete like this, discrete sine wave. So what in the process is it's meant to be continuous in the process, because it's not a signal, it's going to be, it's an analog circuit system. So you have the frequency here. mm, I can make it, let's just put it to be one. Okay. Then phase angle is this is the frequency, one radius. So I can leave it at one radius per hour. Let's just see how it works. So I'm going to save it in case it's not going to work. So you can see it has been how I call it, it has been become a sine wave generator or something. So this is the bias 1000, 4000. So it's going to be increasing by 1000, decreasing by 1000 frequency. Okay. So I'm going to run it and see how this respond. Okay, you know what, with the way this is going, I think we need to do some adjustments to the model. I need to do some adjustments to the model. I'll stop it. I'll stop it. So this, I'll make it to be a sine wave, a fine sine wave. I'll make it to be a fine sine wave and increase the frequency. Uh, can, okay, can reduce it to 0.1. This one is the starting point. Just leave this with the phase angle with this frequency. That means it's it tends to be slower. So let's put it in 0.1. So let's see how it works now. As you can see, this is proceeding correctly. So I'm going to wait till the system stabilize, then now I'll show you how it's going. Okay, the model runs for some times, but it stopped at this point. Stopped at this point, and it's saying that there should be some kind of error or something. Let me close this one. So I think in order to make the model work accurately and efficiently, the sampling time can be adjusted, and the sine wave too can be modeled or something. It might be some kind of box in the solver, the integrator of the Simulink, and the step size that is chose, like as you can see in the Simulink for the model. So that's the trend for the controller, the digital controller, with respect to sine wave perturbation for the system. It follows second order system, or under damped second order system. You understand? Under damped second order system. So because the amplitude is reducing with respect to time as the simulation is proceeding, the amplitude is reducing. So I am going to I don't know if I can reset. Okay, I can reset. So I'm going to save this how will I call it, this perturbation. Then I'm going to go to the other model, the the other system for the continuous system, and do the same thing for the continuous system too. Controller too. Waiting for this one to open. So this is the one that I will use for the continuous controller. So I will delete all this one that is here. So this can be returned back to the. So this is for the controller, continuous controller. Then this will be changed to sine wave. Flip. So configure the parameters: 1000, 4000, 0.1. Then it's going to be continuous. So we can run it and test the response of the model. So I'm going to distribute. So for the continuous system, this is the scope. I see this one, this one. You see, it's more like the other one too. You can see the sine wave. The output of the controller is free. So this is actually more better than what we have for for the the discrete one, and it's faster. So that's the controller response for the continuous system. So assuming you have maybe data on there is the data for the sine wave, the electrical system. For you understand, you can put it at most electrical system can be AC or DC. We tried it for AC, we saw the results. You understand? So for this is actually like this. Yeah, you can see. So it is because it is being reduced. So you can say this is damped oscillation. So it's going to be the as for multiple one, the error is going to be reducing, and you can see the error is not even much. You understand? So you can get faster results, accurate results by tuning the controller parameters, the K and the TI, by tuning it, and then the uh, the control system too. You can design in such a way that it is more very accurate and faster response. I mean, the variable that we are going to be adjusting, you can make it in form of temperature of the coolant. By maybe you fix the flow, then you adjust the temperature of the coolant, so you are going to have faster response for that too. And there are a lot of things that can be done to make the system better than it is now. Uh, okay, so I open the discretized system again and I adjust the sample time. After adjusting the sample time, this is the result that I got from the discretized system. After adjusting the sample time, it was able to run completely, and you can see the response with time, and then you have the results given over here for the discretized system. So I can return it back to 1. Let's see, because I also adjust the sample time of the simulation step size also, the step size of the simulation. So let's see how it's going to work with the discrete the sampling time for the discretization reduced. So let's see how it's going to work. So it's running, it's about to be completed for 0.1. So it's completed. So you can see the at this edge there is no more change in the steps in the response of the controller. The controller is actually stable, but at this, so this kind of response is actually the same thing, like I said, second order damped. You understand? Second order over damped. So I think it's over damped or something. So then we have this response for the system. You can put your cursor over here. So I'm going to save it. And you can now see how to design a digital and analog PI controller for your AEM Electrolyzer system with Simulink and Aspen Custom Modeler software. The integration of the two software make it possible to design a rigorous and realistic system, linear system for electrical component and other dynamic system in Simulink, and the PID algorithm too in Simulink. So you can easily design your own algorithm, do intertwining, do more advanced features like dynamic tuning for your discretized system in Simulink. So with this, I think we are going to be going to the end of this video. That we are going to be this will be the end of this video. So thank you for staying tuned, thank you for joining us, and there will be a quiz. And the quiz is why did I put negative for the KP in this code? The int is based on the response of the controller and the system. So if you are familiar with the controller design in Aspen Plus or Aspen ICs or PID controller design, so you'll be able to answer the question. So why did I put a negative value for for my KP? If I put a positive value for my KP, what will be the influence in my system, my response for my system? And now from the plot, what did you see from the results of the of the system? How does it respond with respect to change in process condition? You understand? How does it respond with respect to change in process condition? When the flow is low, how do you see the response of the controller? So this is what will help you to understand the meaning of the KP that is added for the gain that is given. So thank you. Stay tuned and continue watching our videos and engaging our course content on YouTube on our website. I am your host again, Abdul Babatunde Popola. See you next time.